Now, in our last lesson, we see by comparing the weight with the gravitational pull. Okay, so this equation 1 is the gravitational pull on the surface of the Earth, and it is G m, the mass of the Earth, the mass of the object, divided by the square of the radius. Of course, there's a universal gravitational constant in front. So when we compare with the weight of the object on the surface of the Earth, we only have mg. So when we compare this mg with the term here, the m and the m will cancel off. And we see that the small g here, the small g, is actually the big G multiplied with the mass of the Earth and the radius of the Earth square. So this is the gravitational attraction, or our acceleration due to gravity on the surface of the Earth. So in other words, the small g that we usually use, our 9.8 meter per second, the small g depends on the universal gravitational constant with the mass of the Earth and the square of the radius of the Earth. Okay, so in the next page, I copy down the gravitational here, our g, our small g, the Earth's gravitation, sorry, our acceleration due to gravity. So this acceleration due to gravity is the universal gravitational constant multiplied with the mass of the Earth divided by the radius of the square of the radius of the Earth square. Now this radius, not necessary, if it is on the surface of the Earth, then it is the radius of the Earth. But if it's, let's say, at a certain distance away from the Earth, from the surface of the Earth, you look at the
Okay.
picture here, right? You look at the picture here. Now, if it is on the surface of the Earth here, at this point, right? At this point here, okay, then the r will be the radius of the Earth. Now, however, if it is at a distance very far from the surface of the Earth, this is the surface of the Earth. If the object is at a distance very far from the surface of the Earth, then the distance r will no longer be the radius of the Earth. The distance r will be the distance from the center of the Earth. So this
Okay.
r here, it means the distance from the center of the Earth. Okay or not? The r here. The r here means the distance from the center of the Earth. Now, if the object is on the surface of the Earth, then the r is the radius of the Earth. But if the object is something like a satellite in the space there, then the distance is not the radius of the Earth. The distance is the distance from the center of the Earth. Okay, so now you can read quiz 4.3a.
Response to each statement, true or false. No force or gravity acts on astronaut in an orbiting space station. At 3 Earth radial from the center of Earth, the acceleration of gravity is 1/9 its surface value. If two identical planets, each with surface gravity grams and volume v, coalesce in a planet with volume 2v, the surface gravity of a new planet is 2g. 1 kilogram of gold will be greater value on Earth than the moon.
Okay, right. So we look at the first statement. No force of gravity acts on an astronaut in an orbiting space station. So we refer to the diagram here, right? So this is the orbiting station or satellite or whatever. Now, normally when we look at the video clip or cinema shows, you see the astronaut is floating there as if there is no gravitational attraction. Oh, they ask you, is it true up there in the space here, somewhere in the space station or at the height of the satellite, there is no gravitational attraction? True or false? So the answer is false. Even at a distance way above the surface of the Earth, maybe three times the radius of the Earth, or maybe not so, maybe about a few thousand kilometers away from the surface of the Earth. Now, even though it is at that level or at that distance away from the center of the Earth, there will still be gravitational attraction. And this gravitational attraction is actually very much weaker than the gravitational attraction on the surface of the Earth because the distance is very far away. Then you may ask, if there is a gravitational attraction, why the astronaut cannot fall back to the surface of the Earth? And not only he didn't fall back to the surface of the Earth, but he appears to be floating in the air like that.
Mm-hmm.
Why? Now, the reason is because the gravitational attraction is counterbalanced by the centripetal force. Now, as you know, this satellite or space station, they are orbiting around the Earth. They
Okay.
are, in fact, rotating about, orbiting the Earth. That means they are rotating. They are moving in a circle around the Earth. Now, when you talk about moving in a circle, there will be a centripetal force. So this
Yeah.
centripetal force is countering the gravitational force. So as a result, the net force is zero. That means there appear to be no force acting around. But there are two forces. The only thing is that these two forces, they balance one another. That's why the man is looks quite free up in the space station. So answer is false. There is gravitational attraction, very much weaker. This force is countered by the centripetal force. Okay, we look at question before I move on. Any question on this A?
No questions.
No, no. No, then we move on to the second statement. At three Earth radii from the center of Earth, the acceleration due to gravity is one ninth its surface value. Okay. Now this one, it has to be exact, so we have to use mathematical treatment because they say it's 1 over 9, one ninth of the value on the surface of the Earth. So let's see whether it is exactly 1 over 9 the surface, the value on the surface of the Earth. Okay, right. Again, we are going to use this gravitational pull, the G, the acceleration due to gravity, and we are going to make use of this relationship. The acceleration due to gravity is the universal gravitational constant multiplied with the mass of the Earth and the distance away from the center of the Earth. So the R here is not the radius of the Earth, but the distance from the center of the Earth. Okay, so we apply this formula. I copy down this formula here. So if it's on the surface of the Earth, then it will be G, capital G, ME divided by R square. Okay, but now we are talking about a distance three times the radius of the Earth. It is three times the radius of the Earth. So I replace the R here, the red color R here, with three times the radius. Instead of one R, it is now 3R. It's now 3R. So I dare not say that this is the G on the surface of the Earth. So I say at 3 radii away. So at 3, so this G is not our 9.8 G. It is the g at 3 times the radius of the Earth. Okay, so this is the new g. It's not our usual g. So when you square the 3, it becomes 9. When you square the r, it becomes r squared. So when you take out the r, sorry, when you take out the 9, it becomes 1 over 9. And the g you put back inside, it is still g me over r squared. But there's a 9 in front there. Because of the 3 square, there's a 9 there. And because it is at the bottom or at the denominator, so the 9 will be at the bottom. So it is true, okay? At 3 times the radius of the Earth, away from the center of the Earth, the gravitational pull is only 1 over 9 that of that on the surface of the Earth, right? So you just substitute 3r into the formula and you will get 1 over 9 there, right? So true, the second statement is true. Any question on this